Hey, good morning, everybody. All right. Yeah, Corey, thank you, Corey. So, um, thank you, Marco. Thank you, Ronald. Well, on a Thursday, you have your first test, which of course covers chapter 13 and whatever we have done in chapter 14, including uh, what I will lecture today. So a lot of you are concerned about the test and how I'm going to um, do it. So here's how. I usually give the test when I teach in person in the class for the class time. The class time usually is at 1 hour and 15 minutes, right? Um, but uh, and always it is closed book, closed notes, everything. Okay, but in this case, I'm going to upload the test at 8 o'clock, right? 8 in the morning, and you will have until 11 to write your test and send it to me. Okay, I'm giving you 3 hours and that should be more than enough. As I said, when I teach in person in the classroom, I only give the class time, which is hour and a half, hour and 15 minutes. So that is how it's going to work. I give you the instruction when I uh, upload the test. Uh, any comment, any question? No question. Okay. So I was talking about integration theory, and I sort of covered sections 14.1, 14.2, and 14.3 and 4 are very uh, connected, very easily can be covered. And I asked Abraham on Friday to talk about 14.3. Okay, let's check. Um, but here is the uh, a quick review of integration theory, uh, which the highlight is Cauchy's theorem. Okay, Cauchy's integral theorem. And Cauchy's integral theorem works this way. You have an analytic function in a simply connected domain. There's no hole in here. And as soon as you have a closed curve and you integrate over a closed curve, the answer is 0. Because that's the Cauchy-Goursat theorem, all right? Then we have Cauchy integral formula. See, in this case, f of z, the function that we are integrating over this curve, doesn't have any bad point at all. If there is a bad point, the bad point is outside this closed curve, all right? So you get 0. The question is, what about the case when the bad point is inside that curve? If the bad point is inside that curve, then here's the bad point inside the curve. The result is going to be 2 pi I f of that bad point. All right. What is f? F is the remaining part. So you just ignore z minus z naught. Whatever remains, that is your f. Evaluate f at that bad point. So this is Cauchy's integral formula, right? Well, I'm not going to prove it for you. I'm going to give you a bunch of examples to practice this one, okay? And all right. So, and then there are some very interesting consequences of this Cauchy's theorem. One of them is that as soon as the function is analytic, which means it has derivative in a simply connected domain, then the function has also antiderivative, all right? As soon as the function has derivative, it also has antiderivative. And the antiderivative actually is this. You choose a fixed point and define f of z to be integral from z0 to z. And since the function is analytic, the value of this integral doesn't depend on this curve. You can go, you can choose any curve you want, all right? All right. So then we have, this is the Cauchy's integral formula one more time. And when the bad point right here, z naught, has power 1, okay? What if here you have parentheses and you have a square? Well, that will be Cauchy's integral formula for derivative. And here is Cauchy's integral formula for derivative, right? So you have a bad point, sure. The rest is fine, but z naught is a bad point. And z naught has an exponent here. If the exponent is n plus 1, so we have this formula, okay? And we can calculate this integral. How do we calculate this integral? Well, you multiply by inverse of this. So the integral from on this circle of radius r. And again, another consequence of Cauchy's integral theorem is that it doesn't matter. You choose this one or a bigger one, all right? The integral over outer circle is, or outer boundary, is the same as integral over inner boundary. So, Cauchy integral formula for derivative, which is this one, but we always want to find value for this. So what is the value for that one when you integrate over, let's say, c And inside C, you have this bad point. So here's f of z, which is nice part of the function, right? F of z is analytic. We don't have any problem with f of z, but we have problem with z minus z naught, which is in the denominator, n plus 1. And the integration, of course, is a closed curve going counterclockwise. The answer would be 2 pi I over n factorial. Oh, remember, this is n plus 1, but here is n factorial. The nth derivative of this good part of this integral, the function, evaluated at that singularity, evaluated at z naught, okay? So this is how we calculate this type of integration, integrals. So there are three important theorems. One is Cauchy integral, Cauchy's theorem, Cauchy-Grosset theorem, which says, look, if the function doesn't have any bad point, the integral is 0. That's the best one. The next one is Cauchy's integral formula. If you have just a single bad point here, the answer will be 2 pi I, the good part of the integrand, evaluated at z naught. I'll give you a bunch of examples to see. And this is the second important one. And here is the third important one, which Cauchy integral formula for derivative. And this is the one that we will use. You want to integrate over a closed curve, and the bad point is inside, okay? The bad point is inside. So the question is, when you have a power here, what happens? So the answer is 2 pi I over n factorial. This function, the good part of the integrand, dz, of course, evaluated at that bad point. All right. So three important facts. For example, here is an example. What happens if you have z minus z naught squared? Oh, well, based on this formula that I just showed, here is the formula. See, you have n plus 1 here. So n is 1. When n is 1, on the other side, you are going to have f prime of z naught, 2 pi I f prime of z naught, okay? All right. If this is 3, then you are going to have f double prime, of course, that n factorial also will be involved. So if you have 3 here, n is 2, okay? When n is 2, you have 2 pi I divided by 2 factorial, which is 2 and 2 cancels. You get pi I, and here n is 2. So the second derivative evaluated at z naught. Good. Of course, we have, when you look at this theoretically, see what happens here. Let's analyze this formula. I am integrating over this curve, okay? F of z is analytic there, but I'm getting the nth derivative evaluated at z0. So when the function is analytic here, on a simply connected domain, whatever, and you integrate over that closed curve, you actually are finding the value of derivative. Not only the first derivative, second, third, and goes on, all right? So as you see in this case, we only have a function, which is analytic. But this formula gives us derivative and derivative of all orders. So one theoretical consequence of this formula is that as soon as a function is analytic in a simply connected domain, analytic means derivative exists. But, based on that theorem, not only derivative exists, second, third, and you name it, all sorts of derivative will be there, okay? All sorts of derivative will be there. Okay, good. Time to have examples. Hey, do you have any question about these three major facts? Cauchy-Goursat's theorem, Cauchy integral formula, and Cauchy integral formula for derivatives. Do you have any question about these three? All right. I don't see any question, so let's go and get some examples. All right, let's start with this one. I want to evaluate this integral. Sine z divided by z squared plus pi squared. On this curve, what is the curve? Oh, here's the curve. Oh, you need to be able to read those curves. You need to, as soon as you see such a thing, right away you should realize this is a circle. Centered at 2i, here is 2i. With radius is 2. So this is the circle. We are integrating over this circle. Centered at 2i, radius is 2. Okay? Well, I'll look at this. And I am going to put this, although it is implied by, but that little circle means we are integrating over a closed curve. Well, do we have a singularity here? Do we have a bad point here? The bad points are the zeros of denominator. And sure, zeros of denominator are right here. You take pi squared to the other side, and you get z equal plus minus pi I. So pi is 3.14 or something, all right? So it is within. Pi I is right here. It is inside this curve, negative pi I is outside. So I'm not really concerned about negative pi I. It's outside. So this is the integral. I can write this as product of these two. So we don't have any problem here. So I can consider this as good part of the function divided by z minus pi I. Okay, and this is the good part of the function. This is the part that is analytic. We don't have any problem with this part. And this is what I call f of z, the good part of the integram, the part that is doesn't have a bad point inside. Oh, here is the bad point, pi I. So based on Cauchy's integral formula, this will be 2 pi I f of z naught, all right? This is the Cauchy's integral formula. I'm going to apply this to this function. F is this one, the good part. So the answer is 2 pi I. Evaluating this at that bad point, so it would be z of pi I divided by pi I plus pi I, which is 2 pi I. 2 pi I cancels. So the answer is just pi sine of pi I. Okay. Any comment, any question about this example? Oh, please pay attention, very, very closely pay attention to these examples because it gives you the better understanding of how you're supposed to apply those formulas. And besides, you're going to have questions of this type on your test. Okay. Well, here is the curve. What happens if you have two bad points? Now, in this case, we only have one bad point inside, right? The other one went outside. So what if we have two bad points like this? Well, in this case, you say, look, the integral over this curve is integral over this one plus integral over this one. And then you apply Cauchy's formula. So Bill Dodson is asking why is sine s over z plus pi I, right? Well, here's the function though. I just wrote this denominator z plus pi I times z minus pi I. And we are integrating over this curve, okay? The bad point, which is inside the curve, is pi I. But negative pi I is not inside the curve. So this will not concern us. So what happens I'm going to separate this. Just put the bad point in denominator. All right? So this is another way of writing this. I am putting this, right? If you multiply top and bottom by z plus pi I, you get the same thing. Why I am doing this? Because the bad point inside is this one, pi I, not negative pi I. All right? And I am preparing this integral to make it in the format, in this format, so that I can apply this. So in Cauchy's integral formula, in this format, the numerator is a very good function, is analytic. It doesn't have bad point inside this curve. So that is what I'm doing. This is the part that I will call f of z. Doesn't have any bad point inside this curve. And then I will apply this formula, all right? Okay? Does it make sense? Del? All right, good. So could we have both of these to be bad point? Yeah, if you consider a curve, a bigger curve, then you have to consider, like this one. If you have two bad points inside, we don't care about a bad point outside, all right? Suppose we had also this Z3, another bad point outside. Oh, we don't care about this. We don't care about this one. We only care about those singularities that are inside this closed curve of integration, or that curve of integration also called contour, right? If we have such a case, then we will write the integration over that outer boundary is integral over the sum of the integrals over inner boundaries. And I told you why when I was talking about Cauchy's theorem, where the region is not simply connected, the region has a hole in it, all right? Okay, let's have more examples. I'm glad that you're asking questions. And with these questions, I'm sure things will be more clear. Here's another example. I'm going to give you a bunch of examples to make sure that you understand what's going on. Okay. So this is the function that I'm going to integrate. Obviously, we have a bad point, right? Z equal I is a bad point. Now, if this is outside the closed curve that we are integrating, we know it will be 0. But when it is inside, we need to apply that Cauchy integral formula for derivative. Now, here's the closed curve. Again, it is a circle centered at I, radius 1. So I is inside. Here is the curve over which we are integrating. It's a circle centered at I, radius is 1. So the bad point, I, is inside. If that is the case, we need to use Cauchy's integral formula for derivative. Okay? Cauchy's integral formula for derivative. Let me show you one more time. Here is Cauchy's integral formula for derivative. The good part of the function, the bad part. If the power is 3, that means n is 2. N is 2, replace n by 2. You get 2 and 2 cancelled, pi I, and this will be f double prime, the second derivative evaluated at that bad point. Right? So just applying that formula, since it is 3, n is 2. So you do pi I if double prime of this bad point. And in this case, the bad point is I. See, we don't have any problem with this. This is your f of z. This is the good part of the integrand, which is analytic nice. So it will be based on this formula. It will be pi I. Second derivative of e to the z evaluated at I. But e to the z is a nice function. Its derivative is itself. So the first derivative is itself. Second derivative is itself. So it will be e to the I. Pi I, e to the I. Okay, that's the answer. Any comment, any question about this example? Any question about this example? All right. Right. Del Dodson has a very, very good point. Very good point. Instead of saying discontinuity, which is true, we call that point. Let's use that internationally accepted term, which is called singularity. All right. Yeah, you're right. So let me give you another example that matches Del Dodson's comment. Suppose same thing, right? Same integral. Let's bring it down. Okay. All right, here. Suppose we want to evaluate this, e to the z minus I to the third dz over a curve C. Okay, what is that curve C? Closed curve, gotta be closed. Oh, here's the closed curve C. C is z minus 1, 1. Oh, look at this. This is a circle centered at 1, radius 1. So here is that circle. Centered at 1, radius 1. So this is y-axis, this is x-axis. Here is 1. And the bad point is right here, is outside. When the bad point is outside and you are integrating here over this curve, and the function is beautiful function in this area, the bad point is outside. So what happens? The answer is 0. Cauchy theorem. Okay? The answer is 0. We will be in trouble if that singularity, or Del Dodson says discontinuity, fine. If that bad point is inside the curve, if it is inside the curve, then you're supposed to use either Cauchy integral formula or the Cauchy integral formula for derivative. Okay? Does it make sense? Well, doesn't. All right, all right. Now I'm glad that you made that comment. It's very, very related to the topic. So if the discontinuity is outside, we don't care. The integral is 0. But if the discontinuity is inside the closed curve, that is when we use Cauchy integral formula for either derivative or what. All right, here's another example. C is the circle centered at 0, radius 2. Well, just give you a little picture of this curve. Sorry. Centered at 0. Here 0. And radius is 2. And I, unfortunately, is inside. I is inside. Okay. As soon as the bad point or discontinuity is inside, then you got to use the Cauchy integral, especially when you have power here. You need to use Cauchy integral formula for derivative. And the answer here is going to be 2 pi I divided by 3 factorial, the third derivative of the good part of the function. All right, this is the good part of the function. And good part of the function here is z. What is the third derivative of z? Oh, well, it is 0, so the answer is 0. Okay, here, the good part of the function is very simple. So the third derivative is 0, so that is why the whole thing became 0. The integral, the value of integral became 0. Okay. All right. Any comment about this example? Brandon, yeah, please be careful about using terminologies. It is the third derivative, all right? The third derivative of f evaluated at that singularity. So in this case, it just happens that f of z is this one, but it could be something else. If it is something else, you call it f of z, of course, then it will be the third derivative of the function evaluated at that point. All right? Okay. Any other comment or question? All right. I'm going to give you, as I said, more examples to understand how you should apply these formulas. Oh, here's one. It's a good one. I want to integrate this guy over the circle. Oh, look at the circle. Centered at I. Here is I. The radius is 1.5. So it goes up to here and goes 1.5. So here is 2.5, right? So this is the circle. We are trying to integrate over this. This is the function. See, there are some singularities here. The zeros of denominator are what we really are concerned about. All right. Del Dodson is asking a question. What if the closed, I guess he meant the curve. What if the closed curve isn't something simple like a circle? A good point. Very good point. Well, when I was talking about Cauchy's integral formula, okay, let me explain this part, which is very important. So Cauchy-Goursat theorem says F is analytic in a simply connected domain, okay? And if that it's here, simply connected domain, any closed curve, doesn't matter how bad it is, integral over that closed curve is 0. And that is when you do not have any bad point. The function is completely analytic, right? Has derivative. What if there is a hole in there and we usually construct that hole ourselves? So here is a curve. I want to integrate over this curve, but it's a very weird curve, all right? As Bill Dodson says, what if it is not a circle? It is a very weird curve. And this is a bad point. We do this. We create this hole in here, all right? And if you remember, I had a cut here, a cut there, and I proved that if this is a curve C and this is a bad point, and the function is beautiful function in here, all right? The integral over that weird curve is the same as integral over the circle. Okay, let's call this one C1. So what if we don't have a closed, we have a closed, very weird closed curve? Well, if there is a bad point here, we isolate that. And based on Cauchy integral theorem for non-simply connected domain, where there is a hole, integral over this will be the same as integral over this one. And in that way, instead of that very weird curve, we convert the integral over a circle. Okay? We convert over a circle. Okay? Is it clear now, Gail? Okay, good. And here's the situation. We are integrating this function over this curve. It could be a very weird curve. That's fine. What are the bad points here? The zeros of the denominator. Z equals 0 is a bad point right here. Z equal I and negative I. Here is another bad point. Here is another bad point. But this bad point is outside. We don't care about that. So there are indeed two bad points that we are really concerned about. So what do? We say the integral over the big circle is the same as integral over this C1 plus integral over this C2. Okay? And that is what we did. And then the advantage of doing this is that in either one of these, if we are integrating over this C1, which is this one, we only have one bad point, and that is 0, because the other one is outside. And if you are integrating over curve C2, there is bad point I, but 0 will not be the bad point anymore, okay? All right, so here is what happens. I am integrating over C1, and the only bad point is 0. I is not the bad point, so I will write the function this way. So this is your f of z now. And this is the singularity. And then it comes to integration over C2. Integration over C2. I is the bad point. 0 is not, right? 0 is not. So we will only take z minus I in denominator. The rest goes up. Okay? We write it in this fashion. So z minus I is a bad point for this here. And then you apply Cauchy integral formula either for derivative or just Cauchy integral formula. For this one, the bad point is I. You evaluate this f of z the f of z is this one, an I. For this one, the bad point is 0, and you have a square. As soon as you have a square, you need to use Cauchy integral formula for derivative, and this one will be f prime, but f prime of this guy, derivative of this guy. And if you compute this, that's what you get. Okay? Any comment, any question about this example? This is a very nice example. Gives you a better understanding of that Cauchy's integral theorem. Okay. Now, Krish is asking, why did I take derivative? And that comes from the associated formula. Here is the formula. When you don't have, when the exponent here is 1, you don't have derivative. But as soon as the exponent is 2, means n is 1. N being 1, it is derivative at that point, all right? So I'm using this Cauchy's integral formula for derivative. So this is the significance of this example. In this example, I use 3 important facts. 3 important facts. Got to understand those facts. Fact number 1. Fact number 1. Instead of integrating over this, I am going to integrate over this circle and this circle. Fact number 2. When you are integrating, here you have a square in the denominator, z squared. You gotta use Cauchy's integral formula for derivative. Fact number 3. Here, the bad point, z minus I, has exponent 1. If your exponent is 1, then you don't need derivative. You just evaluate this function at that bad point. Okay? So this is the significance of this example. I used 3 facts, 3 important facts that we learned in integration theory. All right. Any comment, any questions? So here's another one. Again, how many? I am repeating this formula for you. Krish, be careful. If the bad point is outside this curve, it is 0. Cauchy's integral formula, because this function will be analytic nice function in this area. The bad point is outside. You don't care. The integral is 0. If this bad point is inside, then like this one. Okay? Like this one. Two important facts. You can isolate this with a circle. the integral over the weird curve will be the same as integral over the circle. That's one fact. The second fact, this is when you use the Cauchy integral formula for derivative. So whenever the bad point or discontinuity or singularity is inside this closed curve, and then you got to use Cauchy integral formula, all right? Okay, good. Here is a very interesting consequences of this formula. What if the function is bounded on this curve? If the function is bounded on this curve, and you go to the circle, of course, the integrand, this one, if you stay on the circle, z minus z naught, the modulus, is r, the radius is r. And f is bounded, so this will be upper bound for the integrand. Using ML inequality, then the nth derivative will be the modulus of nth derivative, all right? Less than or equal to n factorial 2 pi I. This is m. Then the length of this curve, and length of this curve, of course, is pi r to pi r, right? So you get this formula, which is called Cauchy inequality, right? Cauchy's inequality. This n is a little bit funny, so I correct that. Okay. And interesting enough, so this is the nth derivative at any point inside that curve. This is Cauchy's inequality. And if the function is analytic, then f prime will be n is 1. So it will be m over r for any r, right? For any r. And as a result, if the function is analytic, this will be true if prime of z modulus is less than m over r, and r can be anything. R, you can let r approach infinity, so f prime always will be 0. As a result, the function will be constant. Okay? Okay. So, one more time. This is Cauchy integral formula. It doesn't matter how many times I repeat because of its significance. So, Krish, be careful. The bad point is inside. The bad point is inside, and here we only have z minus z naught, no more exponent. This is Cauchy integral formula. But what if the bad point is inside, and here you have an exponent? If you have such a thing, then it will be the nth derivative stuff that is called Cauchy integral formula for derivative. All right. All right. Distinguish between these two, please. Okay. right? And here is another example. So when exponent is 2, it will be 2 pi I f prime evaluated at this bad point, all right? Like this one, another example. So this is the good part of the function, the integrand, analytic, nice. So it will be your f of z is this one. So it will be derivative of this function evaluated at 1, of course, multiplied by 2 pi I, right? So here is derivative evaluated at that point. So the answer will be okay. When the exponent is 1, it will be just the function evaluated at that point, all right? When the exponent is 2, it will be derivative evaluated at 1 and derivative 4e. So the answer will be 4e. Okay. Well, if we are integrating over that circle, all right, maybe, okay, I make it this one. It will be 4e 2 pi I, so 8 2 pi I times this. Now, it just happens that in both cases, we got the same. No, in fact, this is f prime. I need to make sure. Okay, let's see. If you have just z minus 1, it will be f of z evaluated at 1, which will be e. So 2 pi I e. In this case, pi I e. Okay, but if you integrate over this, which is circle centered at -1, then the bad point will be outside. Then the integral over this one will be 0, all right? Will be 0. Okay. Any comment, any question? I gave you enough examples. So, yeah, there are more examples, but I think if you just concentrate on those, that would be fine. And here's the Cauchy inequality. As I said, when the function is analytic, R can approach infinity and f prime will be 0, f will be constant. That gives us a very good, very important theorem. The theorem says if you have an entire function means it's analytic everywhere, derivative exists everywhere, then that function cannot be a constant. either it's a constant or cannot be bounded if it's not constant, all right? Because in this case, if the function is bounded, for example, it's constant, derivative will be 0 and the function will be constant, right? So be careful that this is one of the major differences between calculus and complex. In calculus, for example, this function has derivative everywhere and it's bounded and it's not a constant function. But you cannot have such a thing in complex. In complex, the only bounded and entire function are constant. This is called Liouville theorem. Liouville theorem, okay? All right, so this will take care of sections 14.3 and 4. And it made sense to learn 14.3 and 4 together